Our next discussion here in the PLC Professor's workshop is ControlLogix. And you see that there are two ControlLogix chassis right behind me. At the moment, I have two processors in this chassis and none in this chassis, but I have an Ethernet bridge card in both, so I can use this as a remote I/O chassis for either one of these processors or both. The nice thing about ControlLogix, it's anything you want, anywhere you want, anytime you want, for any reason you want, literally. Now, ControlLogix is an order of magnitude more sophisticated in its backplane because it is a truly passive backplane, meaning that the backplane is nothing more than a 32-bit parallel network, and each module that slides into the backplane, that connector on the back of the module is a communications port that communicates on the control net type network or protocol that runs on the backplane. So let's get into this lab, and there's a lot to discuss with ControlLogix because the I/O modules are also an order of magnitude more feature-based, have a lot more features than the 1769 or any of the other I/O modules. So let's discuss your lab project that you completed. Welcome to the next lab discussion video. This video is the next in the sequence that supports an introduction to RS5000 Volume 1, the first volume of the complete PAC Learn series. The ControlLogix lab can be found approximately on pages 128 through pages 139. ControlLogix, as opposed to CompactLogix, is a different hardware platform, but it uses the same Logix engine that CompactLogix uses. ControlLogix Basics with RSLogix 5000. This video is going to be very similar to one that's already on YouTube, which I think I called Quick Start or Jump Start RSLogix 5000 with ControlLogix. However, this specific video is going to follow the lab that is in the manual. Creating a new project, building your data house or structure. First, we're going to create a new project, and we go to File, New, and we want an L75. Most of us aren't going to have this hardware anyway. You might have an older processor. The L75 is the newest, the most powerful. Version 21 is the newest, and version 21 actually only supports the L70 series and the new CompactLogix L1, Y2, and 3. But we're going to stick with the older 17 through 20. So we're going to pick version 20. We're not doing redundancy. Redundancy will probably show up in volume 3. Redundancy is a very complex subject. And we're going to call this processor my CLX. And if you haven't realized it by now, CLX is the contraction for ControlLogix, and CPX is the contraction for CompactLogix. It really doesn't matter what size chassis that we pick, other than that you realize you can have 4, 7, 10, 13, 17, and then this is a particular a special chassis. But typically what you're going to see in the field is 7, 10, and 13. I see very few 17-slot chassis and very few 4-slot chassis. So we'll just leave it the default 10-slot chassis. And it doesn't matter what slot you put the processor in, but we'll put it, let's see, what do we do in the lab? I had to put it in slot 1. And I think the reason that they typically do that with ControlLogix is to emphasize the fact that you can put it in any slot you want. And we're going to put it in slot 1, otherwise our lab structure wouldn't match. So we're going to put it in slot 1 just like we did in the lab. Click OK. It says already exists. Do you want to replace it? Actually, no. Instead, that reminds me that I didn't browse and pick a location to store my projects, which I normally have you do. I'm going to have you jump out and find Learn RS5000. Remember, I had you create a folder called Learn RS5000 and have you put your projects in there. Now we'll say OK. You may have noticed I had a subfolder in there that said Archive for Recording. So because I use these names over and over again, I have to keep moving the files into another folder. Otherwise, I'm going to keep getting this already exists message. So here we have our project. And you have a backplane and you have a processor, and that's it. Now this all looks the same as it did with CompactLogix so far. So let's click on Controller Properties, go to Date and Time, and this is going to look slightly different. If we were going to do motion, we would want to check this box, Enable Time Synchronization. If you don't check this box, you won't be able to do motion applications with your controller. But we're not going to check it because we're not doing motion. Then I had you go to the Advanced tab. Here we see something called System Overhead Time Slice. The default is now 20%. It used to be 10%. In the beginning, 10% was the default, but over the years they found that 10% was never enough. The System Overhead Time Slice, this percentage here, determines how much resources go towards the continuous task and how much goes for everything else. This is not the lab for this subject. That will be probably in volume 2, where we discuss system overhead time slice in greater detail. We'll actually probably do a presentation on it. Also, click on memory, and this is a memory estimation tool, and it shows estimated I/O memory and estimated data and logic memory. There's two separate sections of memory. We have quite a chunk of free memory for I/O, and you can see more than 30 times that much for data and logic. As you go through building your project, not this project because there's so little in this, you're not going to put a dent in any of this. If you're actually doing a project, you can, as you're going, go look to see the estimation of how you're using your memory. Most folks don't run out of memory with the L75. Okay, the next thing we're going to do is we're going to configure some digital I/O in the local chassis. So I'm going to go ahead and close this. Because of the screen size that I picked, I can't go down to the bottom and click OK. And the reason that I'm using this screen size and limiting it is to keep it at 720p, so it looks a little bit better. I'm going to move this up so we can still see the menu, and see there's still not enough space here to raise this up. We can just see the edge of the buttons down there. Matter of fact, I think I could probably, we'll just click on OK there to get rid of it. If you were doing this, you would see all those buttons down there. Okay, so we want to add some digital I/O. In the previous labs for CompactLogix, we may have used version 17 or version 20, and the version 17 pop-ups are slightly different. The menus, the configuration boxes are not quite as intuitive as they are in version 20. However, they still perform the same function. Now we realize that you might be using the 90-day free version of RSLogix 5000, which at the time of the creation of these labs was version 17 only. If you're using version 17, the images for the set of labs will look slightly different, but not so much different that you cannot still do these labs in version 17. So I'm using version 20 for the most part. This will give you a little taste of both ends of the spectrum for the versions used in the field. Version 17 and 20 are the most dominant. Okay, so first we want to add a digital output module. So we would go to the backplane, right click, new module, and this is where version 20 looks a little bit different than version 17. In version 17 you didn't have the selection of these filters. Now I know I want an OB16D. I could unselect all of the filters, select just Allen Bradley, select just digital, and that reduces the list down. But still, you see there's quite a few in here. But there is the OB16D right here, and I can select it there. However, because I know what kind of a module I'm going to select, I'm going to go ahead and check these boxes, and I'm just going to type in up here in the search field OB16. Okay, see, now I've greatly reduced the choices. I know I want an OB16D, so I can double click here, or I can click and hit create. I just realized that that might have been off the screen. I need to pay closer attention. Here are the filters that I unchecked, and then I selected digital. There's OB16D. Then I reselected well, it really doesn't matter what I select for filters here. I'm going to clear the filters, and I'm going to type in OB16. Now, if you're adding I/O modules, it's because you have these modules physically, or they're on order, they're part of your project. It's not like you have to open up these categories and set filters to find what you want. You can just type in the part number or a portion of it. You notice I didn't type in 1756. And I didn't put the D on the end because I knew that OB, as a matter of fact, if I back up a little bit further, just OB, back up a little further, that's too many choices. So OB filters it down so you can see everything in this one spot. And if you put in 1 for 16, it's narrowed down, and putting in the 6 isn't going to narrow it down any further. So you get the idea. So we're going to click on that, hit create. The rev level, we're going to leave it 3 because we're not actually doing a lab with ControlLogix. If you have a ControlLogix, then you can do this lab, and if you have the hardware. I don't have this hardware, so I'm going through and showing you the process of creating the project and adding I/O cards. But I don't actually have these cards. Okay, now I'm going to name this DC outputs in slot 0. DC 00. Okay, and it's in slot 0. And we want full diagnostics output data. I always disable the keying. In this case, it's really not going to make any difference. And if you've forgotten what electronic keying is, it goes by revision level. If I pick exact match, watch what happens right here with the major rev level. If I pick exact match, then it has to be 3 and it has to be 1. If I go with compatible keying, it can be 3 and any of the minor levels. If I pick disable keying, then it can be, this becomes irrelevant. So I typically disable keying when I'm building a system, then I go back later and make it either compatible or exact match. So we'll just leave it compatible because we're not going to actually do anything with this hardware. Notice the Open Module Properties box is selected. When I close that down, it comes up with the module properties. Ordinarily, we would just click OK, we would be done. But I want to discuss these other tabs, which we did in the lab. So click on the Connection tab, which we have open right now. Here's the general, that's what you just filled out. Here's the connection, and this is the RP, the requested packet interval. And remember that all of the modules on a 1756 backplane are a computing device. They have a reduced instruction set processor, they have RAM, and they have firmware. They do their own computing, whereas with the other backplane, like the 1769 backplane or Studio5000 ControlLogix, they were active backplane. The processor, by way of a control bus, would activate one slot, and then it would either push data into it or pull data out of it while the slot was activated. It was all electronic switching. There was no communications on an active backplane. This is a passive backplane. Everybody on the backplane communicates. So what we're telling this output card right now, we are requesting a packet of information every 20 milliseconds. And we can set that from 0.2 milliseconds all the way up to 750 milliseconds. Also, if we're doing commissioning and we don't want this module to bother us while we're trying to work on something else, we can inhibit the module. Also, we may want a major fault on the controller if the connection fails while in the run mode. In other words, if we lose contact, if we lose our connection with this module while we're in the run mode, then we want a major fault on the controller. We want it to stop. So these three things right here are usually addressed when you build your project, whether or not you want to inhibit the module temporarily while you're commissioning some other part of the process. So this won't get left inhibited once you commission, but this will get left checked most likely when you commission your project. But while you're doing commissioning, you may not want this module to crash the whole project simply because there's something you haven't finished yet. Okay, enough said about that. Click on the Module Info tab. Now this tab is not going to show anything because you are not online and in communications with the module. This is actual information from the physical module's memory. Well, we don't have a module. We're not online with this hardware. If we were online, then the module info would populate with data from that actual module. Now this next tab is very important if you're using the diagnostic type modules, which is what we selected. Had you click on configuration, this screen allows you to set the state of the outputs based on the mode of the controller and in the case of a communication fault. During program or fault mode, the controller is not running the control program and therefore not determining the state of the outputs based on input conditions. So the logic is not executing. This screen, or this configuration pop-up, allows you to define what state you want each output point to be in when the controller is in the program mode or if the program is faulted. In the case of a communication fault, you can select whether you want the outputs to behave as if the controller were in the program mode or as if it were in the fault mode. We have 16 outputs here, 0 through 15, and your choice is if I'm in the program mode, I want that output to go on no matter what, or I want it to hold the last state, or I want it to go off. You have to pick one of these three. So when you go in the program mode, hold last state, always go off or always go on. The default is off. If you're faulted, then do I want it to go on, go off, or hold the last state? Of course, off is the default. And you can do that by each individual point. Now, output verify and no load, those are very interesting features of that module. They're there because the module is a computer and the module can monitor itself. So there's a processor in there, firmware and RAM, and in the field wiring side of the optical isolator, if you've been through the previous lectures that were for the complete PLC Learn series, which was done in 500 land, RS500 land, then you know that all discrete I/O modules have an opto isolator between the electronics of the module, or the bus, the backplane, and the field wiring. So it's optically isolated. Well, this module has circuitry on the field wiring side that actually monitors the current flow in the field wiring. So output verify, if that's checked, then when you turn on that output, normally running the program or forcing it, if you turn on that output, the current flow going from leakage up to load current will be sensed, and you can read back a bit back to memory and using your program to verify that the output really did turn on. What you have out there may be a motor starter instead of a solenoid valve. Nonetheless, you turn the output on, this verifies it. If there's no load out there, then checking this box enables that diagnostic. If there's no load, then, and remember, this is all done by current sensing in the field wiring. Okay, and so you could consider these faults if you want. If you turn the output on and you don't get any change in current flow, in other words, it doesn't go from 0 to whatever load current is. Also, no load can sense that there is an open in the wire. In other words, no load current is some leakage state for a solid state output. Both of these perform different functions. One verifies that it went from the no load level up to the load level, and the other one verifies that there is a load there to begin with. In other words, there's continuity through something. And if these fault, you can select whether or not you want to latch the condition. Let's say you have a little, we call it a gremlin, a little gnome running around in your field wiring, and what it really is, it's a conductor under a terminal screw, but the screw is not really tightened down, and as the machine moves or vibrates, it's making an intermittent connection. If that connection is open for an instant, then the no load condition will be sensed and you can latch it. So in other words, you can capture some of these little gremlins. One thing I used to tell customers is if you're going to use 100 OB16s of the 1756 variety in your project, buy at least one OB16D. And then if you suspect that you're having a problem, swap out the standard OB16 with the OB16D, set it up so you can capture these problems. And then once you've resolved it or verified that you don't have a problem, then put the regular OB16D back in and save that diagnostic card for troubleshooting on another day. Okay, next thing, we went to the diagnostics, and here we have electronic fuse, and we reset the latch diagnostics. So here we latch these diagnostics. Here we can reset them from here, or you can actually do this from your program. All these bits are available to read and write in your program. So electronic fuse, remember, if we've got current sensing in the field side of our wiring, then we can perform the function that a fuse would perform. Basically, that means is if we get a short circuit on the field side, then we can open up the circuit, not with a fuse, but by turning it off. Because remember, you've got your output point is basically a switch that you turn on and off to allow current to flow through your load. If the load disappears, meaning shorted, then you can turn off the output, and that's the same as opening a fuse. It's called electronic fuse. You can reset it from here, or you can reset it directly from your program. Same thing with latch diagnostics. Once the diagnostics is captured, you may want to buffer it and then reset it, and then count how many times it occurs. There's all kinds of cool things you can do with this. And then, of course, we have pulse test. If we were actually hooked up to hardware right now, remember, all this is stuff that is really of no value unless you actually have the hardware. If we were hooked up to the hardware right now, this is really cool, and you want to test the wiring. Now, you can't actually test the device, but if we were online right now and we clicked test, it would say pass or fail here, and that would be based on whether or not there was continuity in the field wiring. So when you click the pulse test, the output turns on for a split instant, just long enough for the current sensing circuit to sense that current is increasing, and then it turns it right back off. It turns it on just long enough to see that something is turning on. So you're actually testing that you have continuity in your output. You can see this module would be handy to have. And then, of course, backplane, we don't have a backplane. We have a rack, a chassis that we picked, but we don't actually have a backplane to look at because we don't really have any hardware hooked up. If we were online with the processor, then we could look at the backplane to see what the backplane is saying. So this would be the activity on the backplane. So you can see it's really a pretty cool module. So we'll hit apply. Okay, we really didn't change anything. Well, that adds the 1756 OB16D. Now that we've added that module, let's go look at our module define. And now remember, before we added this card, there were no module define tags. And we've been through this before with other projects. So I had you open these up one at a time to look at them to see what was in there. So this data type, and that is the class of object there, AB colon 1756 underscore digital output 0 data double integer. So even though it's a 16-bit output card, everything is still 32-bit, which means those other 16 bits are just hanging out in the breeze. You can see them in the memory, but they're not useful for anything. But it is still a very efficient way to use memory, to use everything as dense. Okay, so that's all that's in that data type. So if we go to the next one, this is O for output, okay, and it is, that's all you see there, data. So we call this our real outputs here. Okay, now we've got configuration and we've got inputs. You're going, whoa, inputs, this is an output card. We'll get to that in a second. So double click on that. If you go down through here and look, program to fault enable, fault mode, fault value, program, these are all double integers that allow you to individually select. Here's output verify enable, no load enable, etc. This is the configuration double integers. You write to these double integers that are in the output module from your processor, so you can actually change the configuration on the fly. Okay, so we're going to cancel that one, and we'll open up this one. Now this is the inputs coming back from an output module. So here's our blown fuse double integer. If we have a fault, it'll show up on the first 16 bits of this double integer. Remember, this module has an RPI. Remember, we configured that 20 milliseconds. Well, why in the world would a module want to send the processor a packet of information every 20 milliseconds? This is the information right here that is sending back to the processor. The first 16 bits of this DINT are for those 16 output points. Are they followed or are they not? Data, that's the double integer coming back for the data. In other words, what is the state of those outputs? A coordinated system timestamp, we didn't discuss that. We're not going to do that now, but you can capture actual timestamps on the things that are taking place in the output module. Then there's blown fuse. The first 16 bits comes back. Well, the whole 32 bits come back, but the first 16 represent electronic blown fuse, no load, and output verify fault. If the output, if we turn it on but it doesn't turn on, the field wiring, the current sensor in the field wiring doesn't sense it, then it sets this fault bit. So you're going to have really more than one fault bit for any one output. So you've got the first fault double integer, and that is collectively all the faults combined into one. If you had two faults for one I/O point, it would turn on that bit in the fault double integer and in the individual fault double integers. Okay, so I had you look at those three data types there. We'll clamp that back down. As we go through this lab project manual, we start with very little detailed step-by-step pointing to point. In other words, we start with very detailed step-by-step and point-to-point of the interface and gradually reduce the step-by-step, allowing you to exercise your memory and thereby solidifying the procedure in your memory. So in the labs you notice that sometimes I gave you a really detailed step-by-step and then all of a sudden it got skimpy. That's because I want you to be forced to either recall it from memory or go back and look at the procedure and refresh your memory. So the more often you do this, the better. But you will see that in this manual we've repeated some of these procedures more than once. They say it takes 10 repetitions to put it in your memory permanently or for a good length of time. We're not going to do it 10 times. That makes too much paper and ink and make it way too expensive. Okay, next we're going to add a 1756 IB16D module. Okay, so now we're going to add an IB16D. So we might as well cancel to get rid of this. So we're going to go to our backplane, right click, new module. I always wished I had the game show music to play while I'm waiting for something to show up on the screen here. I'm just going to type in IB. See, they got rid of quite a few things. And notice that the check marks change too. So we go to 1, bang, see, nothing but digital left. Of course, putting in a 16 isn't going to change anything. So IB1 brings up what we want, IB16D. So you see there are 4 versions of the IB16. This is the standard module, the least expensive one. This one's more expensive. Now this is isolated, which is going to be more expensive than the standard, but I don't know how it stacks up price-wise with Diagnostic. And then there's the sequence of operation. That's a real cool module. In a later version or a later volume of the manual, remember this is volume 1, there's definitely a volume 2. The material, all of the labs are pretty much done for volume 2. I have not started anything for volume 3, so maybe in volume 2, if I can squeeze it in, or volume 3, we can look at sequence of operation. That's a cool module. Okay, so let's pick the IB16D. We can double click. We'll leave it at version 3 and we'll call it DC underscore inputs, and it goes in slot 2. Now why are we going to slot 2? Not because it says slot 2 here, but remember our output card is in slot 0 and slot 1 is our processor, and of course our project knows that, so it's always going to bring up the lowest slot number that's still unused. If we had used slots 4, 5, 6, 7, and 8, it would always come up slot 0 until you use slot 0. So it always shows the lowest unused slot number. We'll leave compatible keying and we'll click on OK. Now Open Module Properties is checked. Click on OK. This is no different than what we saw with the output card. Now remember, with the output card, the requested packet interval was for information coming back as to the status of the outputs, not of inputs. In this case, this RPI is a little more important because this is how quickly that input card is going to get on the backplane and send the information to the processor's I/O memory. Now this is one thing that really sets the 1756 passive backplane apart from an active backplane. In an active backplane situation, the processor has to stop what it's doing and it has to go and get the inputs, put them into memory, and then run the code, executing the code against that snapshot of the inputs, sets the outputs, then has to stop what it's doing, send the outputs out to the output modules one at a time. In this case, when the system boots up, basically, I'm going to paraphrase here a little bit. When the system boots up, it goes out and looks at its hardware configuration over here. That's what we're creating, a virtual hardware structure here. It looks and goes, oh, I've got an OB16D in slot 0. It goes to slot 0 and it says, hey, slot 0. Now remember, slot 0 is an address, a physical location on the backplane that the processor can communicate with. Not activate, but communicate with. It sends a message and makes a connection to that slot and says, hey, are you an OB16D blah 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 version this and that? And that card answers back, yeah, that's me. And then the processor says, great, you have an RPI of 20 milliseconds, you have this, you have that, and it gives all the configuration details to that card. Then it goes back to the I/O tree here and it goes, oh look, in slot 2 I've got an IB16D. So then it goes and it sends out a message to slot 2. It says, are you an IB16D? If you are, then here's your lineup. Then once the processor goes in the run mode, these modules are out there doing their own thing, but they're updating the memory in the processor at the RPI. Now later on you might hear API, actual packet interval. That's when you start doing rack optimization and you start doing different networks with remote I/O. If you have an RPI of 20, or we'll say of 40 milliseconds, you might end up getting an actual of 30. Typically you will always get an actual RPI that's faster than the requested, and of course it would have to be that way. Engineering wise, it wouldn't work for you to be expecting 20 and only get 25 or 30. So you'll at least get what you request and maybe more. Okay, so here's our IB16D. This pop-up doesn't look any different than the output module. We already did the general. We named it, slot number, etc. Connection. Module info, you're not going to see anything there unless you're online with that module. In that module, then it populates these fields. Now configuration, remember this is the diagnostic module. This has got some cool stuff, just like the output card did. Enable change of state. That is exactly what you think it is. Remember, there's a RPI of 20. So every 20 milliseconds or better, this input card is going to send a packet of information out onto the backplane that is addressing the processor location. And it will populate double integers or a data structure in the processor. And those data structures, we saw those over here in module defined. It will populate those with information from this module. Now, if you have selected change of state, and right now these are all selected, so I'm going to deselect them so there's no change of state selected. So let's say I go and I pick for input 1 off to on and for input 3 on to off. What I'm basically saying is this is the configuration that I send to the input module when everything fires up and boots up. I'm telling that input module, I want you to send me every 20 milliseconds the status of this module, including all the field wiring states. And if at any instant input 1 goes from off to on, or if input 3 goes from on to off, I want you to inform me right now. Drop everything you're doing and send me all 32 bits. In other words, if you're going to send data back to the processor, you don't just send 2 bits. You send the whole word. Enabling change of state is enabling or telling that input card to update its image, its snapshot, in the memory of the controller every 20 milliseconds, and anytime input 1 goes from off to on, and anytime input 3 goes from on to off. Okay, well, that's pretty cool. We'll put that back the way it was. Typically, I don't use change of state unless I have to, because that eats up more backplane resources. So I typically turn those off. If you don't need to know instantly, why gobble up backplane information? I believe that it's explicit instead of implicit in the communications on the backplane. Nonetheless, it eats up bandwidth. Okay, enable diagnostics for open wire. Well, remember that like with the output card, there's current sensing on the field wiring side of the opto-isolator. So again, if we have a proximity switch or any solid state input device, photo eye, prox switch, whatever, a output point on a drive, any solid state device hooked to an input that's going to turn that input on and off, there's leakage current. So the current sensing in the field wiring side can sense that leakage current even when the input is off to say there's an open wire. And then of course, if these are all selected, what is the case where this would not work out too well, where you would get a fault when there was no fault? Well, when does an input actually have an open? Well, if you have a normally open dry contact or normally closed, every time it goes open, you have an open wire. So you don't want these checked if you have dry contacts. Now, if you only have one dry contact and it has to be for input 2, well then uncheck that. So input 2 won't give you a fault for a dry contact. And of course, there's no reason to latch that. Oh, one other thing, input filter time. Now, this is like a debounce, okay? And you can do it, you can debounce from off to on or on to off. And you can do it for no debounce at all, 1 millisecond or 2 millisecond. All it is a filter that ignores any change of off to on unless it is greater than 1 millisecond. It ignores any on to off condition unless it's greater than for 1 millisecond. So a little spike of noise, and if you're at all familiar with the difference between the on state and the off state for like 5-volt TTL. I don't remember all the details, but I think anything less than 2 volts or 1.5 volts is considered off. Anything greater than 3 or 3.5 is considered on. If you have a weak signal for whatever reason and a noise spike comes along, it could drop that on voltage down below the on state or vice versa for the off state. So that's what these filters are for. Default is 1 millisecond. Okay, diagnostics. Here you can reset any of these conditions. Well, there's only one, open the wire. You can enable the latching here, and you can reset it here, or you can reset it from your Logix. And then, of course, the backplane is not going to tell you anything because you're not online. So we'll select OK. So there's our output and input module. Now that we've added that input card, let's go back here to our module defined. Now you can see we have 2 more classes of objects. And see, here's our digital DO, digital output. Here's DI. Here's the actual data that's coming back. Now remember, the main data from an input module is the data coming back. Right there, data. But this also includes defaults, coordinated system, timestamp if you're using that, and open wire. So there is only one fault. So if you got an open wire fault, you got a fault. So these 2 words right here are probably always going to have the exact same value. But for future improvements, changes, new firmware rev levels for this module, you may get a new firmware level that gives you another feature that would be right here. It's another type of fault, and so this fault word would be collective for both this fault and any new faults. You get the point. And then of course here's the configuration. Filter times, change of state disable, and then here's the individual settings for change of state on to off, change of state off to on, fault latch, and open wire. Okay, that pretty much concludes our setup for ControlLogix. So the big difference between ControlLogix and CompactLogix is the backplane. With ControlLogix, you can have 32 tasks. Each task can have 100 programs, and each program can have an unlimited number of routines. The number of routines really limited by how much memory you have. Obviously, when you run out of memory, you run out of memory. But you're probably going to run out of ideas for routines before you run out of memory. With CompactLogix, some of them don't support this many tasks. Some of them, I think, support as few as 4 tasks. But you know what? I have never seen more than 4 tasks in any application out there in the field, even when it was an L75 with dozens of I/O cards, servos, and everything else. I've never seen more than 4 tasks. Now, inside of each task, I've seen many programs. Typically, I see a main task that's continuous, like you see here. Then I see a periodic task or 2 periodic tasks, and then I might see an event task. But typically, it's a continuous task and 2 periodic tasks. That's pretty much typical what I'm seeing. Thank you for watching this lab project discussion video on the ControlLogix platform, configuring it using RSLogix 5000.